So welcome all. I'm going to explain to you how to find height of a absorber. Okay. So this is the equation, right? Z is the height. So HTU times NTU. HTU is this GS over KYA. So this KYA is given GS, you know, gas flow rate based on solid free gas flow rate. So this one you can find. Now the main job is to find this integral. Okay, dya over ya minus ya star. So this integral you have to find it numerically. So that's the main point of today's discussion. So ya2 ya1. So this is gas exit concentration. This is gas inlet concentration. This is small. This is big, right? Bigger. So you have to integrate this. Ya is the data point on operating line. Ya star is data point on equilibrium line, right? So Ya minus Ya star is basically the driving force for mass transfer. Okay, so how to find this integral numerically? Okay, so let's see. So what you have to do, you know Ya1, Ya2. So from equilibrium data, you can plot this equilibrium line. Okay, then what we have Y1, Y1, uh, Y2, X2. So Y2 is the exit concentration. So from where to where you want to reduce. So Y2, X2 and Y1, X1 should be given, or you will use material balance to find it. Uh, okay. So once you know this data point, this just from two data point, okay, Y2, X2 and Y1, X1, you can connect it. Okay, with a straight line. Then we need to integrate from this point to this point. Okay, so what we will do, we need to find this Ya minus Ya star. So starting from Y1 to Y2 or Y2 to Y1. Okay, Y2 is small, so we can go from Y2 to Y1. So Y2 just drop perpendicular to the equilibrium line. Okay, that's because basically Y2 star. Okay, so at this point this is Y2, this is Y2 star. So then we can find Y2 minus Y2 star. Then in this range we have to, because we are going to integrate numerically, so we have to break into the interval. So now you will do a hand calculation. You cannot make like too many intervals. If you make as many as interval, your result will be more accurate. Okay, so for that we can use like MATLAB or something, but numerically you can make interval of like 0.1 or something like this. So starting from y2, we will make go to y1. So get the y2 y2 star. Then we can take next data point. Any data point you can take in this range, and then it will read the y2 star next. So this is y2 again, and read the y2 star, and so on. So then find the y1 over y minus y star. Then in this integral is with respect to y, right? So y minus y star, isn't it? So ya minus ya star. So this will be, you have to plot numerically. So 1 over this versus y. So you will plot this. So from y2 to y1 on x-axis, and y-axis you have 1 over y. So now we are going to calculate the integral numerically, means basically finding the area under the curve, right? So how you will find area under the curve? So y2 and y1 you have different interval, isn't it? So this is the delta y. So and this is basically rectangle with this is some error here. So what we'll do, we will find this is delta y, we know y2 and next y, delta y, and then we find the value of 1 over y minus y star. So this value at this point and this point, this two. Okay, we take the average of this two value and then you multiply with this delta y. So this will be approximate area of this rectangle, okay, with some error. So if we make very small, then we will not have error. Okay, but in numerical, if you're doing a hand calculation, of course you cannot make like too many. So you may have like 10 interval. That's it. And next this. So again, value of this at this point and this point, take the average and multiply with this interval, and so on, and then finally you will sum them. So summing the area will give you the integral. Okay, so so this is the equation. So let's solve this equation, this question. This is very similar to the one in your slide. So problem statement, we solved similar before. So absorb, temperature, pressure given, diameter. Okay, so this is the inlet gas flow rate G1 in volumetric flow rate, right? So from volumetric flow rate to molar flow rate, how we can find, as we did before, PV over RT, gas law. So this is volumetric flow rate. Okay, and then this is that's become G1. Okay, also L1 is given, so you need to convert this into mole, is gram per second. This is KYA. Okay, the STU we can get from here. Ammonia concentration to be reduced from 0.9 to 0.008, right? So this is a small y1 is 0.09 and a small y2 is 0.008. From this we will get capital Y1 solute free, okay, and capital Y2. So capital Y1 is 0.09 divided by 1 minus 0.09, right? Similarly, capital Y2 we will find. Okay, so you can see the solution. As I said, Ya1, capital Ya1, capital Ya2. Xa2 is 0 because this is solvent is pure. Solvent is ammonia free. Water is pure water. There is no. So X2 coming from the top is only water. L2 is only water. Xa2 is 0. So now we need to find Xa1. Okay, we know Y2, we know Y1, we know X2. So only one is unknown. And then in the meantime, you find the GS and LS. So GS is G1 1 minus Ya1, right? GS is the molar flow rate of gas um, based on solute free. So there is no, we will subtract whatever the ammonia is here. Okay, makes sense. So GS and also LS, LS is 1 minus X2, X2 is 0, so it will be same. Okay, so LS GS you find it, then what we have, LS times XA2 minus XA1 equal GS Ya2 minus Ya1. So LS is known, GS is known, XA2 is known, Ya2 is known, Ya1 is known. We can find XA1. So what will be the concentration mole fraction of insolvent leaving the absorber? Okay. So XA1 is known. Now we can XA1 is known, Y1 is known. So what we can do? We can draw XA2. XA2 is 0, right? XA2 is 0. XA1 we have calculated from here. You can see XA1 is this. Okay. So now xa2 is 0. So xa2 ya2, and then y1 is more, right? Y1 x1 xa1, this one. So just connect with the set line, and then we will have something. This is equilibrium line. Okay, so we need to integrate from y capital Y, from this. Yes. Okay. um, so what we need to do, we will start from here. This is y2, y2 star. Get rid this one. This is y2 star, right? Similarly, we have this data point. Read this. Get y2 star. Read this like this up to the value of y1. Okay, so here is the solution. You can see uh, this is the y2. Okay, this is y1. So you can see, I can show you a different one. Yeah, like this. Same. So you can read at each data point. Okay, so at each data point you can read y1. So from starting from y2, and then next interval we will select from all. So for example, ya2 was 0.008. This is fixed, right? So next interval we can select as you want. So if you can see here, is like 0.008, then 0.01, then even with interval of 0.01, it goes up to 0.9. So for example, 0.01, 0.01, and then you go read here 0.01 on y-axis. This is operating line, right? So now, so this is go up to this equilibrium line and read corresponding star. So at these data point, so these are the values of y star. So get all these values, then subtract ya minus ya star. Okay, then find 1 over ya minus ya star. So now see, the integral is what? So if we make it like, if we make it numerically, basically it is ya minus ya star, sorry, minus, and then this is basically delta ya delta. So we need to get those deltas, right? So this delta difference, so delta y, so dy or delta ya in this interval, so which is basically in this case zero point 0.02 minus zero point 0.01. So sorry, zero point 0 zero point 0.01 minus zero point 0. So first delta difference of y is this, so that's zero point 0.001. Then zero point 0.01 to 0.02 to minus zero point 0.01, 0.02 minus zero point 0.01. So this is zero point 0.01. So these are the delta y. Okay, at this delta y, these are the value of 1 over y minus y star. Okay, now this graph is not there. So what we, okay, so 1 over minus, so what we need to do, as I told you, so we have something like this. So at one data point, first one and second one, suppose, so this is the delta y, we know, right? And then this is the value of, this is 1 minus ya minus ya star. So this is one value, this is one. So what we need to do, this multiply by half value of this. midpoint. Okay, then we can get the area of this rectangle closely, not approximately. So what we need to do, these two values, okay, so these two values we take the average. Okay, first two, then next two, okay, then next two. So these average, you can see. So 125 plus 119. So you can see here. Then 119 and 121. So okay, and then 125, and yeah, these values are same. Okay, okay. So these average is calculated with, and then delta y is there. What you do, you will multiply both delta y times average of this. So you can see it's very clear here. Okay, and then you find the sum, you add all of them, and then that's your NTU. So height will be GS over KYA. This is HTU, and NTU you multiply, you get 5.48. So I mean, if you do this is numerical, so everyone will do, if he will get little bit different values. There's no one answer close. Yani, this is numerical, reading error is there. So you may get, someone get may get 5.3, someone may get 5.2. So because of the reading from the graph and doing it numerically. Okay, so this is the way you find the height of absorber. Okay, so hope this will help.